Hi, welcome everyone to the Spectral Geometry in the Cloud seminar. We have the pleasure of having Dorin Bucur from Université Savoie Mont Blanc, and he will speak about maximization of Neumann eigenvalues. So, Dorin, the floor is yours.
Thank you very much. Thank you very much for inviting me to give this talk here. So it's really a great pleasure for me. So I will speak about the maximization of Neumann eigenvalues, and this is an ongoing work with Éloi Martinet, PhD student, and Edouard Oudet from Grenoble. Let me tell you what's the context of this problem. So I will always work in Rn. So I will discuss only eigenvalues of sets in Rn. And I consider omega open, bounded, and Lipschitz. So for now, omega is smooth enough so that the spectrum of the Neumann Laplacian consists only of eigenvalues. But from the beginning, I want to say that omega, I will not suppose it connected. So omega may be smooth, nice, but may have several connected components. So that the zero eigenvalue for the Neumann Laplacian appears several times. So I consider the Neumann Laplacian on omega. And under the hypothesis that we set, omega is open, bounded, and Lipschitz, we know that the spectrum consists only on eigenvalues. I start counting with 0, but as I say, because omega is not necessarily connected, 0 may appear several times. And of course, some eigenvalues are counted with their multiplicity. And I just recall it because I will use it several times. This is the variational definition of the kth eigenvalue of the Neumann Laplacian on omega via the min-max principle of the Rayleigh quotient. For here, the minimization is done in the class of subspaces of dimension k plus 1. K plus 1, this is why our counting starts with 0 in h1 of omega. And our problem that we want to try to solve, or at least to gather some information, is to maximize the kth eigenvalue of omega among all subsets of Rn of a prescribed measure. Alternatively, I can write the same problem because of the homogeneity of the eigenvalue for rescalings. I can write it as the maximization among subsets in Rn of the product, the volume of omega power 2 over n times mu k of omega. So this is the key topic that I want to focus on. And the questions to which we try to give an answer are the following. So first of all, is it true or not that there exists some set omega which really maximizes mu k of omega among all subsets of prescribed volume? And this is the existence question, which is the main focus of this talk. Unfortunately, I will not be able to give a very good answer at the end, as you will see. And in general, there exists a second question to which we would like to answer, which means that we want to find some qualitative properties of these optimal sets if they exist. Like, for instance, regularity of the boundary. Is the boundary smooth enough? Is the boundary very smooth? Or possibly some other kind of properties. Is the optimal set symmetric? It has a hole, does it have a hole? Or maybe it is the ball or not. Otherwise, if we are not able to do this, we can at least try to make some sort of numerical approximations and to have an idea on how this best shape, provided it exists, looks like. And clearly, this question of maximizing, as I say, the volume of omega power 2 over n times mu k of omega, it's related to the Polar Conjecture, which is stated here, which just say that the mu k of omega is bounded from above by the leading term in the Weyl asymptotics. And you see, if I want to maximize this product, volume power 2 over n times mu k, in fact, I'm trying to search whether or not this set omega is satisfying the inequality. I can try to do this. If, for instance, one is able to prove some qualitative properties of this best shape, provided it exists, then possibly there could be somehow a step forward proving the Polar inequality. Now, the question is how to deal with this problem. A priori, when you want to maximize mu k of omega in the class of sets, you would say that this is a shape optimization problem. And somehow in France, when you say shape optimization, maybe you have to think as an engineering problem, because those kind of problems came from engineering questions at the beginning. However, as soon as we want to go into fine properties and to understand whether or not the best shape exists, some tools of analysis have to come into the game. and we wonder what kind of tools. And if I have in mind two strategies. The first one is to use some free boundary techniques, which worked very well for problems with Dirichlet boundary conditions. I will recall immediately some facts about it. So if you, instead of Neumann boundary condition, we want to deal with Dirichlet boundary condition, tools borrowed from the techniques of free boundary problems can really help to understand it. If instead of Dirichlet boundary condition, we would like to work with Robin boundary conditions, we have to turn on what are called free discontinuity problems, and we have to use a package of techniques which is of completely different nature, and then which are really very adapted to Robin boundary problems. However, if we want to work with Neumann problems, with problems which have Neumann conditions on the free boundary, there is no tool. Up to my knowledge, there is no really a strategy how you can attack and deal with this kind of problem. And for this reason, this kind of problem is very difficult. And let me say some word, because you see, free boundary problems work very well for Dirichlet boundary conditions, and free discontinuity techniques work very well for Robin. And what's the main difference between these two types of boundary conditions and Neumann? There is something which is somehow related to what happens at the boundary. If we speak about Dirichlet or Robin boundary conditions, somehow either asking that u is 0 at the boundary, which is unknown, but u is 0, the eigenfunction, let's say. Or if you ask a Robin boundary condition in which in the variational energy you have an integral over the boundary of u squared. So these quantities somehow put some energy onto the free boundary. This energy onto the free boundary make a sort of effect like the superficial tension, sort of, and somehow this led you to give some information, to obtain some information on these moving boundaries which are unknown, and allow you to play a little bit between the energies which stay on the boundary and the energy of the PDE which stay inside of the domain. In the case of Neumann boundary condition, there is no energy onto the boundary. And this makes the problem very, very unstable. So the conclusion is that I don't have any strategy to offer to attack this problem. And then I want to show you what we have tried and what we have obtained to deal with this. And maybe the best way to understand why this problem is so complicated with respect to the Dirichlet one is just let me to put a little bit in parallel the two problems. Dirichlet and Neumann boundary conditions. So now one slide on Dirichlet boundary conditions. So now I want to work with the eigenvalues of the Laplace operator, but now with 0 boundary conditions. And for this, I take omega, which is a bounded open set, and smoothness here is really not important. And even boundedness is not important, provided the measure of omega is finite. Then in all these situations, so without any smoothness requirement, the spectrum of the Dirichlet Laplacian consists of eigenvalues, which are now starts with a strictly positive one, and I count them with their multiplicity. And the similar question somehow, if I put it in a mirror with the question for Neumann boundary condition, is that I want to minimize the kth eigenvalue of the Dirichlet Laplacian. I have here also the associated Rayleigh quotient, which stands in H1 0 of omega instead of H1 of omega. And equivalently, so I want to maximize the lambda k among sets with prescribed volume, or I can write it in this scale invariant manner as I want to minimize the product between the volume power 2 over n from delta k. And again, this minimization question is related to the Polar Conjecture, claiming that lambda k of omega is greater than this quantity for every omega in Rn. So now this problem here, Dirichlet boundary condition, I want to minimize the kth eigenvalue. For Neumann boundary condition, I want to maximize it. The problem looks very, very similar from some point of view, but let me now make this comparison here and tell you what is known and what is not known. So here you have Dirichlet boundary condition. You want to minimize lambda k with prescribed volume. Here you have Neumann, and you want to maximize mu k with prescribed volume. And now what is known is the solution, the exact solution in the case k equal 1 and 2 in both situations. So for k equal 1, the minimizer is a ball, and this is the Faber-Cran inequality obtained in the 1920s. And for k equal 2, the minimizer, the solution, is consisting of two equal balls of half volume, equal and disjoint balls of half volume. And this was proved by Cran and Seger after the 20s. The similar question for Neumann is again known. So for k equal to 1, the maximizer, it's a ball. This was proved in 2 steps by Seger in 54, I think, in the class of simply connected sets in 2 dimensions, smooth sets in 2 dimensions, and by Weinberger in 56, I think, in general in Rn in the class of Lipschitz sets. However, as soon as you want to pass to the information for the second Neumann eigenvalue, things are a little bit more complicated. In the Dirichlet case, looking to the minimizer for lambda 2 was a kind of not very complicated problem, because this came back to understand the positive and negative parts of a second eigenfunction. So, and immediately it came back to the classical inequality now for lambda 1. While the same question here for the maximization of the second eigenvalue, it's not trivial at all. It was solved in 2 steps. The first step was a proof by Girold, Porterovich, and Nadirashvili in 2008 in 2 dimensions in the class of simply connected sets. And in 2019 by Antoine Honroy and myself in Rn in the class of Lipschitz sets. And now, this is not a consequence, an immediate consequence of the same inequality for k equal to 1. These kind of inequalities usually work like this. You have a domain, you want to get some comparison between mu2 of omega and mu2 of one ball, let me write it in mu1. And then the idea is that you look to an eigenfunction onto the ball, and somehow you extend suitably the eigenfunction, and you produce a test function over omega. So that's the strategy. So you take a suitable eigenfunction or a package of eigenfunctions over the ball. By some suitable extension, you put them over omega, and you search good position such that the traces of these extended functions become orthogonal to constant. For instance, if you want to look to mu1, and then you test mu1 of omega with this. So that's the strategy. Now let me point an important question which will come a little bit later. You see, in this strategy, in this proof for the maximization of mu1, that's the strategy of Weinberger, the regularity of omega doesn't count at all, but really at all. I mean, if this is Lipschitz here or not, it doesn't matter, because we just compute some sums of traces of, let's say, smooth functions, which are the eigenfunctions on top of the ball, that we look on omega. So if omega has cusps, for instance, or it's even less than Lipschitz measurable, this computation can be done. And this is a crucial point that will come back in my talk. Now, what happens for the other questions? So first of all, existence of a solution. Well, in the case of the Dirichlet eigenvalues, we know that an optimal domain does exist. And the proof came in 2 steps. First was a result by Butazzo and Dalmaso in 92. They proved the existence of optimizers for this problem, provided omega is subset in some fixed box, which is bounded. And in 2011, there were 2 different proofs for the existence without the restriction of the box in Rn. And you see, it took something like 20 years to make the step from a box to Rn. And this question will appear again now for Neumann boundary condition. However, here we don't know whether or not optimal solutions exist. This is the main purpose of my talk, to try to prove the existence of a solution. So this is a question to which we don't have an answer. Regularity of optimal sets. Now, for Dirichlet boundary conditions, now we know that optimal sets do exist. And the question is to try to understand their regularity. And there are already really good information about the regularity of those optimal sets. So for instance, except K1 equal 1 and 2, where we know what exactly the solution is. But now we know that, for instance, optimal sets are bounded. We have some control of their diameter. We know that optimal sets have finite perimeter. We have some control on their perimeters. We know that optimal sets have a singular set which is closed on the boundary. Outside the singular set, the boundary is C1 alpha, and the singular set is of lower dimension. So there is some information on the regularity. For Neumann, in fact, already we don't know the existence of a solution, but we don't have a strategy to prove regularity. And I will tell you why. Now, stability of the spectrum, what means here? So in general, for Dirichlet boundary condition, if you have a sect omega, and if you consider some perturbation of it, I mean a rough perturbation, omega epsilon, to know whether or not the spectrum is stable for this, let's say, rough perturbation, whatever the perturbation is. And the answer is, well, we know really what happens. We can decide from the knowledge of the geometry whether or not the spectrum is stable. For this, we have to look to capacity of the complements in balls, for instance. If we have good information on how the geometry moves, we know immediately whether or not the spectrum is stable. The similar problem for Neumann boundary condition is that, well, in some very particular situation, we know that the spectrum of the Neumann Laplacian is stable. What means very particular situation? For instance, if you take a Lipschitz set and somehow you perturb the boundaries in the class of Lipschitz set with the same constants, with uniform constants. And in this case, the spectrum is stable. However, as soon as you get a little bit out of these very, very, let's say, smooth and uniform perturbations, the stability completely fails. So in this case, I would take omega, and then you can just fix a point onto the boundary, fix a very small neighborhood, and you can produce local perturbation around this point, and you can completely destroy the spectrum of the Neumann Laplacian of omega. So there is a result by Hempel, Secco, and Simon on this, which roughly speaking says that you can introduce into the spectrum any compact set in 0 plus infinity. So a small perturbation completely destroys the spectrum of the Neumann Laplacian. So this is very unstable. And continue my list of results. So for the Dirichlet problem, a very important fact which is known and which is helpful in the proof of existence is the so-called relaxation by gamma convergence. What is this? This problem is close to the stability, but it's set in a different way, in the sense that now I have a sequence of sets. These are, let's say, arbitrary geometries in the space. I don't know, whatever you want as a geometry. And then starting from this sequence of geometries, one is able to construct a sort of geometric limit by some compactness argument. A sort of geometric limit, which in the case of the Dirichlet problem is very well understood. The results are essentially due to Dalmaso in Moscow in late 80s. One built a measure, a positive measure mu, and one can prove that the kth eigenvalue on the moving domain on omega n will converge to lambda k associated to the measure mu. So how this acts? So is mu, so comes like this, is minus Laplacian u plus mu times u equal to lambda k u. And here mu, it's a Borel measure. It may be infinite on some regions, and this encodes the Dirichlet boundary condition. The good point is that all of this passage is completely understood. So given any sequence of domains, one is able for some subsequence to build the measure mu and to fully understand the behavior of the spectrum. The similar question for Neumann is not known. There are only some particular situations coming essentially from homogenization, in which case you have let's say a set omega, and you perform uniform regular holes distributed in a periodic way. And in this case, you can follow what happens with the spectrum. But in general, for arbitrary sequence of domains, this is not known. And to finish with this, let me say some words also for the numerical approximation. So the first numerical approximation of optimal sets for the Dirichlet eigenvalues are due, up to my knowledge, by Edouard Oudet around 2003. Since then, there were several groups of people who worked from different perspectives with different tools, and numerically they tried to approach the best geometries for K, starting from 3 to 10 to 15 to 20, and so on. What one can observe is that the results are quite stable, and subsequent different computation would generally lead to the same results. This is not really the case for the best approximation of Neumann eigenvalues. So I have in mind at least 3 series of computations. Among all, every time was something which was not as before, some geometry which was not as before. So here I will show you the latest computations that I know. These are due to Antunes and Oudet in the book edited by Antoine Henrot in 2017. And you have the maximizers for mu k. Here is mu1, and as expected, it's a ball. The maximizer for mu2, as expected, it's a union of 2 balls. So these are numerical approximations. And here you have optimal sets for mu3, mu4, mu5, and so on, up to mu10. So previously, there were computations by Antunes and Freitas in 2012 and by Amandine Berger in 2015. And for this and that, the shapes were stable. However, starting from the 5th, the same geometry was not obtained by different computations somehow. So now the question is what really happens? And here you have also some computation now in 3 dimensions of the space by Antunes and Oudet in 2017. So the question is that we want now to find whether or not we can prove the existence of those geometries, and if we can say something on them. And the answer is not that positive. And before starting, let me make some historical point. So I just recall that the first result is due to Seger in '54. He proved in 2 dimensions that in the class of simply connected smooth sets, the disk is maximizer. Weinberger in '56, the ball maximizes in Rn in the class of Lipschitz sets mu1. Girouard, Nadirashvili, and Porterovich in 2008, the union of 2 equal disjoint disks maximizes mu2 in R2 in the class of smooth, simply connected sets. And there is a result by Poliquin and Roy-Fortin in 2010, which says that the maximizer of mu22 is not maximized by a ball or a union of balls. So now, of course, from numerical approximations, we have already know, or we know now that even mu3 shouldn't be maximized by a ball or union. But the first rigorous proof that there exists an index on which mu k is not maximized by a ball or union of balls was by Poliquin and Roy-Fortin. And this is done, I say, easily in some sense, in the sense that they are able to compare this value on union of disks and rectangles, and just observe that on rectangles, they attain a better value. And now there is a result by Antoine Henrot and myself in 2019 for mu2, where we proved that the union of 2 equivalent disjoint balls maximize mu2, here power 2 over n, in Rn in the class of Lipschitz sets. And I put it here and more. And this is maybe the point of what I will speaking now. And let me finish this list just saying that there is a proof by Freitas and Loxen of the same maximality of 2 balls of mu2. using somehow the same package of test functions, but with a different and maybe more classical topological argument. So all these kind of problems in which one has to maximize Neumann eigenvalue and to prove optimality of ball union of balls have at some point to go through some topological arguments, and which are more or less fine. Of course, when you look to mu2, this is more delicate than when you look to mu1. And now let me go and see what this means here, the word more, Lipschitz and more, because if we want to look to the spectrum of the Neumann Laplacian on an open set which is not Lipschitz, we don't have the guarantee that the resolvent operator is compact, so we cannot speak about eigenvalues. But now here is the observation that I said at some point, that in the proof of Weinberger, once you make the process of mass transplantation from the ball towards omega, you don't really look to what the regularity of omega is. You just put some function over omega and you compute some integrals. And then you use these integrals into the Rayleigh quotient to compare it with mu1 or mu2. So that's the point. So we don't really need to speak about regularity of omega in order to speak about the inequality that possibly mu k could solve. And here is what means more from our perspective. So we want somehow to extend the notion of eigenvalue from Lipschitz sets, one definition is absolutely very clear, to densities. What is a density? A density, it's a function defined over Rn with values in 0, 1, which is summable in L1. From the beginning, I tell you the relationship between a density and the domain. So if you have a domain, omega is Lipschitz here, you can see the eigenvalues of this set as to be associated to the density, which is the characteristic function over omega. So this is the density rho I'm introducing here. So the density rho, it's the characteristic function, it's vanishing outside omega, and this one on omega. Now, of course, if I take such a density and I want to somehow to associate an eigenvalue problem, definitely there is no way in which I would be able to define a proper eigenvalue problem associated with this density. So, however, what we can do is somehow to say, no, if omega was a Lipschitz set, the kth eigenvalue is properly defined by the Rayleigh quotient. So let's go into the Rayleigh quotient and somehow to relax this definition on densities. So this is what we do here. We formally say, and I put here a tilde just to say that is not the classical eigenvalue. We can define a sort of, let's say, variational eigenvalue, mu k tilde of rho, as being defined as infimum among all subspaces of dimension k orthogonal functions orthogonal or on rho, functions which are C infinity with compact support. This is an infimum in the class of subspaces, and here it's a maximum for U in S. This is a good maximum because it's done it's taken in a finite dimensional space, while the infimum here is somehow very unclear. We don't know in general whether or not the density rho, for some density rho, this infimum is well attained. Rho coincides with a characteristic function of a set omega, then we are done. So this quantity as we define it here, it's exactly the kth eigenvalue of the Neumann Laplacian associated to omega. If rho is very bad, well, we don't know. This quantity is still well defined, but it will not have an interpretation as an eigenvalue. If rho is, for example, something like that in Rn, again, the mu k of rho has full sense because we can associate a resolvent operator to this Rayleigh quotient, which is compact, and we define spectrum of eigenvalues. But in general, for rho, which is just arbitrary, we don't really know what happens. Now, so from now on, I will remove the tilde, and I will continue to call it eigenvalue, although I'm not sure whether or not this will correspond to a classical eigenvalue problem. Why this is important? To try to understand these eigenvalues on densities. It's important because somehow a consequence, or within the proof that we got with Antoine Henrot in 2009 for the maximality of mu2, we made that observation that in the transplantation technique of the mass from the ball towards omega, or from two balls towards omega, the regularity of omega was really not important. And then we observed that if somehow we replace omega by a density and we put down this definition of mu1 and mu2 for densities, the inequalities continue to hold. This is the Weinberger inequality for the first eigenvalue, and this is our inequality for mu2. So mu2 on a density rho may not be very well defined, I repeat, in the classical sense. However, this inequality stands true. So the risk that we take by defining this kind of quantity here with a very non-smooth rho is that mu k tilde of rho is really zero. It may be zero for very large k, possibly for every k in n. However, we want to maximize. We want to maximize, and when we want to maximize, somehow those very bad densities which produce zero relaxed eigenvalues will be eliminated from the maximization process. On the one hand, this inequalities tells us that when we maximize in the class of densities, a priori we go above the maximizer in the class of Lipschitz sets, because the class of Lipschitz sets is just a subclass in the family of densities. But now, if we are able to prove the inequality for densities, this means that this should be the correct framework in which we have to search for existence of an optimizer for mu. Also, there is a sort of intuitive conclusion, which can be read like that. So if one is able to prove an inequality by mass transplantation in the class of Lipschitz set, then it should work for densities. Mass transplantation doesn't really care about where we arrive and on the regularity of the set on which we arrive. What are the questions that we would like to answer? The first question is that let's try to look now to the maximization of mu k of rho. So what we know is that this is greater than the maximum of mu k of omega. So it somehow is above. But of course, the good question is to try to look to this problem, to solve it, to prove that there exists possibly a solution for every k, and afterwards to come back and say, no, the best density, it's a domain. It's in fact a characteristic function of a Lipschitz set. But we are not really able to do that. So we want to prove, to look to this problem and to understand whether or not there exists a solution which would be an optimal density in this case. Second, of course, if we know, and that we know now that an optimal density exists, what is the geometry of the optimal density? And why not to wonder whether or not the Polar conjecture could have a chance to hold on densities? Well, why not? So it's a question. Of course, we don't know the proof of Polar conjecture on domains, and now we come with something even more general. But it's a good question. It is a chance or not to prove it on densities. And now let me you realize that I'm going slowly. I start with an easy question to which we don't have an answer. And the easy question reads like that. Let D be a bounded open set. Let's say in 2 dimensions, I take a long, and then I want to maximize just mu1 inside the rectangle. I want to maximize mu1, the first Neumann eigenvalue, for sets which are subsets in the rectangle and which do satisfy a volume constraint. But let me take M in such a way that the ball of volume M does not fit into the rectangle. Let's say this is the value of the volume M. This ball, this doesn't fit inside. Well, this problem, it's a nice problem, is well posed. Can we prove the existence of a maximizer of mu1? The answer is we don't know. We don't really know whether or not inside the rectangle there exists a best geometry which supports the highest value of mu1. So we don't know. However, if one say, okay, but for densities, it is easy to prove it. And the answer is yes, for density, it's relatively very easy to prove the existence of an optimal density. How this works? So the first observation is that for this convergence, let's say I'm taking a maximizing sequence of domains inside the rectangle, omega n, and by compactness arguments, I can subtract the subsequence such that the characteristic functions converge weakly star in L infinity to a density rho. That's the limit in L infinity star of the sequence of the characteristic function. What is really very easy to prove is that mu1 of rho, or in general mu k of rho, it's upper semi-continuous. It's greater than or equal than the supremum lim sup of mu k of omega n. So in general, continuity of the spectrum, it's impossible to get in general without a priori assumptions. Upper semi-continuous is quite easy. So we built a density out of the maximizing sequence. Mu k, mu1 here is above, so it's very good. And the question is, do we still somehow preserve the mass constraint? And the answer is yes, it's trivial to prove the mass constraint as a consequence of the weak star and infinity convergence of the characteristic function. So in other words, we built a density which is better than every domain. So immediately we can solve this problem. We can maximize mu k of rho with a mass constraint inside the rectangle. The proof is the same and it's for free. Even more than that, we can consider functions which are general functions depending on eigenvalue, somehow in the spirit of what Butazzo-Dalmaso did for the Dirichlet. So if f is just, let's say, continuous and increasing in each variable, here you have two examples, the sum of the first k eigenvalues or the inverse of the harmonic mean of the first k eigenvalues, then these functions do fit into the framework. You maximize them, you have existence of an optimal density. Now, this is somehow a sort of toy problem in which we see what we can do and what we cannot do. So we cannot prove the existence of an optimal domain. We can prove the existence of an optimal density. Now, the natural question is what happens if the box is replaced by Rn? Because if the box is replaced by Rn, then in fact, things become much more complicated. And I just recall that the passage from a box to Rn for the Dirichlet boundary condition took almost 20 years. So what happens here? Here again, I want to maximize mu k in Rn. I can pick out a maximizing sequence of densities. This exists. By compactness in L infinity, I can subtract a subsequence which converge weakly star in L infinity to some density, rho. And one can still prove upper semi-continuity. Then what is missing? Well, there is something crucial which is missing, this the constraint which is not necessarily verified. The constraint is not necessarily verified, and this is just a consequence of the fact that the constant function 1 does not belong to L1, of course. From a practical point of view, the density rho here can be the 0. Imagine that you have maximizing sequence for mu1. We know that the ball, this is a ball, and you take one ball and then you translate the ball and you push it to infinity somehow. Well, the ball disappears and the density into the limit will be the 0 density. So this is the mass constraint which is lost. And here I draw two situations for mu2. The mu2, we know the maximizer is the union of two balls. But what happens if the two balls are more and more far away and somehow they are connected by some thin tube, let's say, so that we cannot push them back together. So if you want some focus on the first ball into the maximizing sequence, the second ball will run away to plus infinity. And then in the similar situation for Dirichlet boundary condition, the answer was we can perform some surgery and just cut the tube and then take the two pieces and bring them together. For Neumann, this is not possible. This is just not possible. The behavior in this case in which the two balls are linked by a cylinder, we know that the cylinder will introduce a lot of low eigenvalues, while if the connection is done by a sort of set which has a profile by an exponential function, probably no, not. I mean, we could probably in this case cut, but we don't have any information. So anyway, so this is a complicated part.
I have a question, Dorin.
Yeah, I don't see it.
No, but if you say that this will introduce a lot of small eigenvalues in the case of the tube,
yeah,
then since you're maximizing, it should not happen, right?
yeah, exactly. So this should not happen, unfortunately. And in this case, I would probably like to cut the tube. But what I want to say is that here, I don't know, I cannot cut it, you see, and this really depends on the geometry. For the Dirichlet eigenvalues, in all situations, this could be cut, all situations, you see. So I want to say, sometime you would cut it, sometime you don't, and this really depends on how the thin tube is there. I know how to deal with that. Okay, so now I will maybe go a little bit quicker. And so how do we prove we prove the existence? So we have a sequence of densities of fixed mass in Rn, and we somehow follow the concentration compactness principle of Pierre-Louis Lyon. And there are, roughly speaking, three situations which can occur. The first one, for a subsequence, just says that you can translate the density somehow, concentrating the mass around the origin. Then by compactness, you build a limit density. And then by chance, this is the compactness situation, the mass of the limit density, it's exactly the right one. So this is the very good case, because in this case, this density rho, it's optimal, and we solve the maximization problem. Unfortunately, it may happen that it could happen that there is nowhere concentration of mass. This reads like that. For every positive radius, you take the density rho n, and you search with a ball of radius r, where is the most of the mass of the density, and you just fix it on the highest value of the mass. And this goes to zero. The highest value goes to zero. This means there is no concentration of mass nowhere. And for every translation you make, the weak limit will be always zero. So in this case, we don't build an optimal density. And there is a second situation, like the dichotomy I showed before, which says that provided you make some suitable translation, you converge to some density, but the mass is not zero, it's strictly lower than m. Now, these are the three possible situations. And what we did, we got two results we called the geometric control of the spectrum, which very quickly would read like this. If we have a density of mass m, and if the eigenvalue of the density is quite large, in a maximizing situation, mu k of rho will not go to zero, because it's a maximizing, so it will be high. Then we can prove that there exists a radius which is bounded from above, because this mu k is bounded from below, such that on a suitable ball of radius r star, the mass of the density is bounded from below. And this just say a maximizing sequence can never be in a vanishing situation, because somewhere there will be some concentration on a ball with a fixed radius or controlled radius, because mu k is somehow going high. So there is no vanishing, and we are very happy with this. However, remains the dichotomy situation, which is a real situation. It can occur in maximization. And for this, we have a second geometric lemma, which controls the spectrum, which roughly speaking does the same qualitative behavior as before, but we somehow are able to follow the masses. And we can prove with this second concentration of lemma is that if you maximize mu k, a density may have several mass concentrations, which can be split at distance which go to plus infinity. So the masses are separating somehow. And the number of concentrations of mass is at most k when you maximize mu k, and there is no loss of mass somewhere else. And with this second lemma that I will not detail, so we prove with Éloi Martinet and Edouard Oudet that when we maximize mu k of omega with a mass constraint, we have an optimizer. And I put it in a bracket here, but it's quite important. This optimizer, it's a collection of at most k densities. The k densities and the collection of k densities should be understood as k connected components of an open set. Now, so once we know that we have these global maximizers, they do exist. Now, there are some other questions which come. Is it true that an optimal density is a characteristic function? And we don't know. We are not able to attack this problem even for mu1 in a box. But what we can do, and we did, is that we looked what happens in one dimension of space. Well, in one dimension of space, the shape optimization is trivial because omega open set, it's a union of intervals, and then mu k of a union of intervals, you just look to what are the values, and you can prove immediately that the maximizer, it's a union of k equal intervals of mass m over k, possibly joining at their extremities. That's trivial. Okay, so no difficulty. However, if you look to maximize mu k of rho in the class of densities, now even in R, this is not a trivial question because we cannot prove that the kth eigenvalue of a density, it's a limit of kth eigenvalue of union of intervals. We cannot prove this. Maybe this is false. I don't know. So this problem now we found very interesting, and we didn't find an answer into the literature to maximize in one dimension this quantity. What we found, there is a result by Kroger in 1999, somehow going into this direction. He maximized mu k of rho in the class of concave densities, on concave densities defined on a fixed interval, so there was no mass constraint. And this, he proved that the maximal density is this kind of geometry. It's a piecewise affine density. And now our question is, can we say something in this context with mass constraint and no other information on the density rho? And the answer is yes. We proved this result with Martinet and Oudet, and we proved indeed that the maximizer is again a union of k equal intervals. And in some sense, the maximizer, it's a domain. Well, it's in one dimension. And the equality is attained really on this union of k equal intervals of length m over k. However, the proof, it's not easy. It's not an easy proof to do that. And it requires a fine topological degree argument. Roughly speaking, in one slide, I will just say that we do this we know where we want to arrive. We know that it's a union of segments that we want to have at the end. So we want somehow we look to the eigenfunctions onto the segments, which are sinus functions, and we glue together these k functions. Here you have some draws. Here there are two functions which are glued, which are forcefully glued, like this. And we prove that suitably moving these intervals and gluing them, pushing them, overlapping them, we arrive to build a good test function, which is orthogonal on the constant and or the first k-1 eigenfunctions, and which do satisfy the good inequality for that we want. So it's a classical proof. The difficulty is here that we do it for orthogonality, with such an orthogonality on k functions simultaneously. And here we use a topological degree argument in order to prove the existence of a suitable positions of those segments overlapping, possibly overlapping, which builds the test function. And as a consequence, we obtain for Sturm-Liouville problems of this form some kind of sharp inequality. So we get mu k, the kth eigenvalue for this, let's say, well-posed problem. Just here, you should imagine ρ1, ρ2 are good functions defined strictly positive on alpha beta, and we get this kind of sharp inequalities in one dimension. I'm not sure this was not done before. I asked some of my colleagues, and nobody was aware about similar results. And to finish with that question, is the Polar conjecture true for densities? Well, in one dimension, we just prove it. It's true in one dimension. So the inequality holds. Well, it's not interesting, but it holds. While in higher dimension, the Polar conjecture is not proved in general. And of course, there is an inequality by Kroger, where he proved the inequality involving the principal term appears with a factor here, which is n plus 2 over 2 power 2 over n, which is greater than 1. And the absolutely natural question was, well, are these inequalities of Kroger true also for densities? And the answer is yes. The same principle. Once you work with test functions, if it works on domains, it will work on non-smooth domains and on densities. So this means that probably the Polar conjecture, if it is true for sets, it may also be true for domains. And in the last slides, let me tell you some things about numerical approximation. So you see, we want to maximize mu k of rho, but mu k of rho, it's not a good eigenvalue of a well-posed elliptic problem. And the first natural question is, can we approach them by some numerical tools where you have to solve well-posed elliptic problems? The first guess is to regularize a little bit the density by adding plus epsilon here and there on a bounded box D, a rectangle here, so that you transform the problem in a well-posed elliptic problem. And then you want to somehow to solve this eigenvalue problem, and you push epsilon to 0. And a very bad result occurs. In fact, when you do this, you do not really approach the eigenvalues that you expect for, because you introduce spurious eigenvalues. And here is a typical example where the density was the characteristic function of the ball, and we have a spurious eigenvalues with support outside of the ball. So one has to be careful. And here we inspired from some paper by Aller and Jouve. They use in elasticity for numerical computation. And we perform an approximation with different constants, numerator and denominator, epsilon and epsilon square. And this works. This works. We can prove that solving this well-posed eigenvalue problem, into the limit, we get exactly the values mu k of rho, which are not eigenvalues. This may be only a variational relaxed form of an eigenvalue. However, this is true. Now, the question is, what happens if we fix epsilon and we maximize mu k for the penalized problem with the two values here, epsilon and epsilon square? We can also prove that the formal maximizer that we find here should converge to the maximum of the original problem. And somehow this means that the numerical computation is justified. And now my last slide is to show you what we have done. So these are the results obtained by Antunes and Oudet in 2017. These are the geometry. And I just highlight mu5 here. And I show you what we have obtained. You see, ball, two balls. They are, so the red color, it's 1, blue is 0. Three balls. Well, three balls, you see, there is here some region, a kind of relaxation region. This is the geometry that they obtain in the class of shapes. Here we work in the class of densities, and there is here some sort of passage from 1 to 0. There's the geometry for our density for mu4. This corresponds more or less to this one. However, this is our geometry for mu5. And here is the geometry they obtained. So this is really very different. And here it's very nice to observe that you see the interface inside is sharp. There is no passage, there is no relaxation zone. Well, here the relaxation zone is clear. And then we have this, and maybe here it's mu8, which is nice to look at. And then you have a mu8, which is, so they are really different. There is a relaxation zone inside. So these are the optimal densities. Of course.
Excuse me, Dorin, are the values very different?
Take a look here. That's
okay,
the table. And yeah, so the values are different, but by a slight, very slight value. Okay. Very slight value. So here are the results of Antunes and Freitas. Sorry. So that's Antunes Freitas. And these are our optimal densities. And for instance, if you look, let's look to the mu7, you see, it's 0.3 out of 70, it's like 0.5%.
I have a second question, Dorin. Yeah. If the actual maximizers are relaxed in reality, could you approximate them by domains that are real domains?
No, we don't know. We don't know. So we don't know to prove, we cannot prove that an optimal density or a density, just a density, can be approximated by domains. That's the big failure of what I'm saying. We are not able to solve this step.
In a way, the relaxed problem is not like just a limit of classical problem. We don't know.
No, okay. We don't know. We know this for K1, for K equal to 2. We know this is true for in one dimension in general, but we don't know otherwise in any other situation. And you see, this is my last slide. So really the values are very close. The question is this into the margin of the numerical errors? I don't know. I don't know, maybe not. Maybe this is really the case that, that the optimal geometries in 2 dimensions even for mu3, it's not a domain, it's a density. I don't know, but the answer is that I don't know. So thank you for your attention.
Thanks a lot, Dorin, for the talk. We have some time for questions now. So as usual, if you have questions, either write them in chat or unmute yourself to ask them. There's a question from Rajesh Mahadevan, so you can go ahead and ask.
Yeah, just a short question. So this relaxed problem, is it really a true relaxation, or it's just we have a different
setup?
relaxation?
It's an over relaxation. So it's we don't know the density of the domains in the class of. So the family of densities is not the closure of the family of domains. This is why we call it over relaxation. So it's above. We don't know how far above the maximum over domains. It turns out for K1, 2, it's the same. And in one dimension is the same, but we don't know it in general. Just this would make that the answer could be different. So, I mean, you could have existence of optimal shape for K1 and 2, and maybe not existence for K equal to 3. So, which is maybe is definitely different from the Dirichlet case.
There's a question in chat by Rick Cluggeson asking if you tried computing the eigenvalue for domains that are shaped like a relaxed mu5 shape.
So yeah, that's an idea that we had. Clearly, this suggests that we may try to somehow to cut out a domain, a real good shape out of this geometry and to compute the. So we didn't do that. But of course, this definitely suggests that that the best shape for mu8 is not the one we knew before. I mean, I'm quite confident that we can improve the previous values. I mean, maybe these just say that the best geometry doesn't exist. I don't know. But yeah, that's a good point.
I see that Michael Levitin unmuted himself. So did you have a question, Michael?
No, not really. I wanted, but yeah, that was the question I wanted to ask, whether you tried to start with this funny looking bear for mu8 and try to find an optimizer just for eigenvalue around it and see what happens. So.
No, we didn't do it, but I mean, it's in the program. It's definitely in the program because, but you see, the values are so close to what the mu8. You see here, that's our mu8, and that's the mu8 of Antunes Freitas. They are so close that probably we will not be. We will be somewhere into this cluster of values. I mean, probably it would be better, but.
I have a more generic question, maybe. You know, when you consider densities and you try, it's not a proper problem, but you're getting something which may have continuous spectrum. As you said, you may get zeros all the time, which just means that you pick up bottom of continuous spectrum.
Absolutely.
But for your maximizers, which you pick, do you know whether you pick eigenvalues inside the continuous spectrum or whether you pick eigenvalues below the continuous spectrum, or what's going on?
We just don't know. These values that we define, mu k of rho, mu k tilde of rho, are just variational relaxation of the Rayleigh quotient. So we can in the as soon as rho is not an does not correspond to an elliptic problem, we cannot relate it to the spectrum by any way. So we don't know. We just don't know. We just don't know. I don't have a better answer.
No, it's funny. People in Sturm-Liouville may know a lot about that because they consider it as exotic Sturm-Liouville problem.
Yeah, I saw.
Okay, so there's a question in chat by Muhammadun Gum asking why. He says that you said at the beginning that this kind of problem are not related to shape optimization, and asks why.
No, they are related to shape optimization, but they require. I mean, yes, that's a shape optimization problem, but they require tools which are coming from different worlds, free boundary techniques or free discontinuity techniques.
And there's a question by Alain Didier Nuchegem asking, do we know something about the stability of the maximal density, like an equivalent of Frankel asymmetry or something like that?
So we didn't think to this question. Yeah, it's a question which can be really raised. Yeah, for if you want, we know that the maximizer for mu1, it's a ball in the class of densities, and then yeah, one can raise the question of stability. I don't know. I don't know, but it's a good question. Yeah.
I have a question myself. So I may have missed when it happened, but when you're looking at maximizing in the class of densities, you restrict yourself to densities that lie between 0 and 1.
Yes.
And while I definitely do see why this includes domains, it does. Is there a reason why this is not an actual restriction, or it is an actual restriction?
It is a restriction because of course, if you take a density which takes values in between 0 and 1 and you multiply by a constant, then the problem doesn't change.
Of
but
course.
Where you have to be very careful is to the mass constraint. So the mass constraint works well only if we restrict the density to take value below 1.
So why doesn't it work well with so of course,
because otherwise like this, take a mass which is like that, a big mass, take a small ball and take a density with a constant much higher than 1. It's a constant density. And what you recover, it's mu1 over the smaller ball with the same mass. So if you don't put an upper bound, which is precisely 1 on the density, somehow you cancel the mass constraint. So this distorts the mass constraint.
I was just wondering what happens in a way if you allow singularities in the mass as well, because a priori we really only want the mass to be L1, right? That's the only real requirement of the mass.
But well, if you think to singularities like that, then definitely you have to remove the bound 1, and then it's a different problem. So it's not anymore equivalent somehow to our problem.
Do we have other questions for Dorin?
I have perhaps just one more. It's Alex, just to follow on Michael's question. So you're saying that for the density that you prove exists, you could have, say, mu4 is maximum, but then further I in the spectrum, I mean these eigenvalues, you would have infinite multiplicity, for instance.
Repeat the question. So if
imagine that your density is the maximal one for mu5.
Yeah.
Is it possible then that there is mu10 is of infinite multiplicity, or you can exclude that?
No, I cannot exclude a priori.
Okay.
I cannot exclude it a priori. But definitely multiplicity occurs at every optimal density, but with a finite rank.
Sure, but I mean later on, even for this optimal, you don't know that it's a discrete sequence.
We don't know. Absolutely, we don't know. We just don't know.
Thank you.
That's a problem. I mean, I don't have time to enter the details why it's such a big problem. But really, we can, with our knowledge now, we cannot say many things about it.
All right. Do we have?
Can I ask another question?
Yeah, let's go with Misha.
So, Dorin, could you go back to the definition of your new K tilde?
This one?
Yeah. So you have those powers of rho in numerator and denominator, right? Of course, if you put different power on rho, you would still have this relation that if you take rho to be identity, then it's good. But presumably those are the only powers for which the next slide works.
So you mean if instead of this kind of, let's say, relaxation, I would put rho to the numerator and rho square to the denominator, or something like that?
Yes.
Yeah, it could. I mean, for the existence of a maximizer, there may be a problem because the weak star limit, if rho n converges weak star to rho n square is not necessarily converging weakly star to rho square. So I wouldn't get the same couple rho square into the limit.
I'm more asking about the next slide. Is the next slide you have about this?
So here.
Can you tell right away if?
Here, no, that's the great power. It cannot work with a different power. I don't think so.
Okay, so those are like two powers, one, the only case where this works.
Yeah, I think so. Yeah.
Okay.
All right. Do we have any other question for Dorin? All right. I see none. So thanks again, Dorin, for the very nice talk. And with the amount of questions, I think that I'm not the only one thinking that it was instructive. Next week, we will have a talk by Romain Petrid, who will talk about minimizing combinations of Laplace eigenvalues and further applications. So thanks again, Dorin, and see you next week for everybody.
Thank you.
Merci, Dorin, c'est vraiment très intéressant.